The Space Coast Unmanned Cerberus is a low-cost multispectral proximity sensor. This product was designed to use open-source hardware and software to provide anomaly detection of seismic, acoustic, magnetic, infrared, radio frequency, and visible light spectrums. All information is then transmitted utilizing low-power RF. The Cerberus includes sensors for each anomaly type. It provides high-fidelity temperature and battery status throughout operation. There is plenty of room for future functionality growth due to low utilization of the Raspberry Pi and the Arduino Mega. The data that's transmitted is protected utilizing AES 128 encryption. A single person can carry and deploy the Cerberus within a minute. An Arduino Mega is the key component in both the remote station and the receiver unit. There is roughly 75% memory available for future growth and functionality upgrades. A Raspberry Pi is used to monitor the 9DOF sensor as well as the RTL SDR. There is roughly 70% overhead for future functionality upgrades. The acoustic sensor is a Max 9814 Electret microphone. It has automatic gain control up to 60 dB, which provides a very large sound range. The visible light sensor is a weatherproof camera that communicates via serial. It has motion detection built in and is infrared sensitive. During low light conditions, it uses infrared LEDs to increase the lighting. The infrared sensor is a PIR sensor installed on top of the motion camera. These are commonly found in floodlights and work in absolute darkness. The magnetic and seismic sensor is a 9DOF B&O 055 from Bosch. This is a 9 degree of freedom sensor including accelerometer, magnetometer, and gyroscope. Once the device is initialized, any variation will trigger the device. This includes fast movements such as bumping the unit, but also will detect slow movements such as trying to rotate the sensor. The RF sensor is an RTL SDR. This unit is capable of reading frequencies between 24 MHz and 1850 MHz. Currently it is configured to monitor the FRS radio, commonly found in stores, channels 1 through 7 and 15 through 22. These parameters can easily be changed in the configuration file to monitor any given frequency that is covered by the unit. The telemetry includes temperature and battery voltage. The temperature is provided by a Texas Instruments LM35 analog temperature sensor with an accuracy of 0.5 degrees Celsius. Battery voltage is provided with a resistor divider with accuracy of around 0.1 volts. This is provided over a Hope RF RFM95 transmitter with up to 2 kilometers line of sight range, and AES 128 encryption is used to prevent deciphering the message. The Cerberus is roughly the size of a briefcase and weighs 15.5 pounds. Power draws roughly 4 watts. With the batteries included in the demonstration unit, over 12 hours of runtime should be achieved. In the future, larger batteries can be incorporated and a solar panel can be fitted. If the solar panel is chosen correctly, this should allow the unit to be powered during the day while charging the batteries, extending its lifetime indefinitely in fair weather. This video will demonstrate the assembly process for the Cerberus. Start by undoing the 4 latches on the case. Take the antenna and screw it into the jack on the left-hand side of the case. Make sure it's standing upright when you're done. Take the camera and extend the legs of the tripod. Aim the camera in the direction to be monitored. On the camera connector there is a notch. Index it and push it fully into the connector. Turn the locking ring about a quarter of a turn until the D10 engages. Plug in the battery and close the case lid. Secure all 4 latches and then turn on the power. The unit will start initializing, which takes roughly 5 minutes. This is a screen capture of the receiver output over the serial monitor. Lines 1 through 3 show the initialization status. Line 4 is the cipher that was received, and line 5 is the decrypted message. Line 6 is the RSSI. Higher values mean a stronger signal. Line 8 is the address of the sensor that transmitted the data. Line 9 through 14 shows the status of each individual sensor. 0 means no activity, and a 1 means that there was an activity. Line 15 and 16 show the temperature in Celsius and Fahrenheit, and the last line is the battery voltage. Note the values in the middle of the decrypted message. These are randomly generated to ensure that the same message is not repeated more than once and help strengthen the encryption. This video will demonstrate the operation of the Cerberus. On the left hand side of the screen is the output from the serial monitor for the receiver. It prints out roughly every 5 seconds. This can be changed via the software. As you can see, there was no sound initially, and then as I started talking, we now have a sound trigger. On the right hand side of the screen, I've connected to the Raspberry Pi wirelessly via remote VNC. As you can see, the RF sensor is initialized, and so is the 9DOF. I'm going to transmit using a handheld walkie-talkie that you can get anywhere. As you can see, the RF activity was detected, and it triggered the sensor over the serial monitor. It takes a few seconds for it to clear out. And then once it clears out, you can see the only thing left is my sound. The 9DOF sensor has a magnetometer and accelerometer that measures 3 axes each. It's very sensitive, and it will pick up movements of the sensor itself or accelerations such as a tap or a knock. To demonstrate the seismic alert, you can simply tap the unit. If you happen to move the unit more than a degree or so, you get a mag threshold exceeded. You can see in the serial output that we have a trigger for a magnetic sensor. We've reinitialized. I'll wait for the flag to clear. The flag is clear, and I'll try again to tap it and get a seismic detection. And there you can see we have a seismic disturbance alert, and the flag is lit over here. And the unit is reinitialized. To demonstrate the camera on PIR, it's simple just to wave your hand in front of the unit. As you can see in the bottom left, the camera sensor and the PIR sensor have both triggered activity. This presentation, along with the user manual, can be found on our GitHub repository in the link below, and the external resources used are listed.